on this one. The day's not gonna rest. Who gives his little girls the punishment they deserve?
1, 2, 1, 2, 1, 2. Now this is Blood and Fire. Blood and Fire. You hear that? Yes. We don't play with it now. Don't play with it. Mount Ra versus the Dirty Dread. We come to live this style. Personally. You get me? Step up. I will. Alright. Give me love. I will. Nothing but rhythm as it hits you in the face. Jump to the sound with the drum and the bass. Look up to rock it with the musical taste. No matter what color or even race. Up on the table just to keep them alive. The summer unity, the summer baby survive. The summer system got you rushing up the place. Spinning like a chain and make you up into space. Pull it operator. Whoa. We get to bounce the place to life. Pull it operator. Whoa. We get to bounce the place to life. Pull it my selector. Whoa. We get to bounce the place to life. Pull it operator. Yeah. We get to bounce the place to life. Bring it all the time. Bring it back. Bring it all the time. Bring it all the time. Bring it back. Bring it fire. This is the musical attack. Bring it all the time. Bring it back. Bring it fire. This is the musical attack. Bring it all the time. Bring it back. Bring it fire. This is the musical attack. Change the power from the underground sound. Change the rockers from the deep underground. Rock it on the day of the drum on the bass. Check it, this on the gym, but you're not in the place. See what's up on it, make the crowd so wild. Making them shots and make it up, this is it. You got to be ready with the album heavy. Everybody come to crazy. Pull it operator, whoa. That's the bounce that plays your life. Pull it my selector, whoa. That's the bounce that plays your life. Pull it operator, whoa. That's the bounce that plays your life. Pull it my selector. Look at the bounce that plays your life. Leave it out and bring it back. Bring it fire, this is the musical attack. Leave it out and bring it back. Bring it fire, this is the musical attack. Leave it out and bring it back. Bring it fire, this is the musical attack. Leave it out and bring it back. Bring it fire, this is the musical attack. Love and fire. Run till you can run no more. On the right, I will get you. Oh, yeah. You could I till you can, I don't know. On the right, I gotta get you. Oh, yeah. See, we're gonna be trying to make strong. And we come to measure like it's strong. You get me? Yeah. There's no chance to get some yes. Never coming to go. Still you make me play the wet. Once again, let me rock it on the mind. There's a plan. Bumping the road is red from red. Cause Illinois slash the Lambo. Dropping it down before it's down. From the underground level. No, no, no. Commercialized house is going down with some blow. Just doing the drama. Making sound. Break. Cold like Congo. Fast blasting. Killing them with the panic. Holding in. With a beat with some beat. Bio 6 fanatic. Climatic. Operatic. Static. Pornographic. Automatic. Acrobatic. Psycho-oceanic. Flows. Running the disco side shows. My flow. Buffalo kind of old. Making the one that stick. Quick. Train 6. Drum kick. Yo. Can you?
Chapter 1. The Theory of Interest. One of the first types of investments that people learn about is some variation on the savings account. In exchange for the temporary use of an investor's money, a bank, or some other financial institution In exchange for the temporary use of an investor's money, a bank or other financial institution agrees to pay interest, a percentage of the amount invested, to the investor. There are many different schemes for paying interest. In this chapter, we will describe some of the most common types of interest and contrast their differences. Along the way, the reader will have the opportunity to renew their acquaintanceship with exponential functions and the geometric series. Since an amount of capital can be invested and earn interest and thus numerically increase in value in the future, the concept of present value will be introduced. Present value provides a way of comparing values of investments made at different times in the past, present, and future. As an application of present value, several examples of saving for retirement and calculation of mortgages will be presented. Sometimes investments pay the investor varying amounts of money which change over time. The concept of rate of return can be used to convert these payments in effective interest rates, making comparison of investments easier. Chapter 1.1 Simple Interest. In exchange for the use of a depositor's money, banks pay a fraction of the account balance back to the depositor. This fractional payment is known as interest. The money a bank uses to pay interest is generated by investments and loans that the bank makes with the depositor's money. Interest is paid in many cases at specified times of the year, but nearly always the fraction of the deposited amount used to calculate the interest is called the interest rate and is expressed as a percentage paid per year. For example, a credit union may pay 6% annually on savings accounts. This means that if a savings account contains $100 now, then exactly 1 year from now, the bank will pay the depositor $6, which is 6% of $100, provided the depositor maintains an account balance of $100 for the entire year. In this chapter and those that follow, interest rates will be denoted symbolically by R. To simplify the formulas in mathematical calculations, when R is used, it will be converted to decimal form, even though it may still be referred to as a percentage. The 6% annual interest rate mentioned will still be referred to as a percent. The 6% annual interest rate mentioned above would be treated mathematically as R equals 0.06 per year. The initially deposited amount which earns the interest will be called the principal amount and denoted P. The sum of the principal amount and any earned interest will be called the capital or the amount due. The symbol A will be used to represent the amount due. The reader may even see the amount due referred to as the compound amount, though this use of the adjective compound is independent of its use in the term compound interest to be explored in section 1.2. The relationship between P, R, and A for a single year period is this formula. In general, if the time period of the deposit is T years, then the amount due is expressed in the formula, this formula. This implies that the average account balance for the period of the deposit is P. And when the balance is withdrawn or the account is closed, the principal amount P plus the interest earned, PRT, is returned to the investor. No interest is credited to the account until the instant it is closed. This is known as the simple interest formula. Some financial institutions credit interest earned by the account balance at fixed points in time. Banks and other financial institutions pay the depositor by adding the interest to the depositor's account. The interest, once paid to the depositor, is the depositor's to keep. Unless the depositor withdraws the interest or some part of the principal, the process begins again for another interest-earning period. If P is initially deposited, then after 1 year, the amount due according to equation 1.1 with T equals 1 would be P times quantity 1 plus R. This amount can be thought of as the principal amount for the account at the beginning of the second year. Thus, 2 years after the initial deposit, the amount due would be this formula. Continuing in this way, we can see that 2 years after the initial deposit of an amount P, the capital A will grow to this formula. A mathematical purist may wish to establish equation 1.2 using the principle of induction. Banks and other interest-paying financial institutions may often pay interest more than a single time per year. The yearly interest formula given in equation 1.2 must be modified to track the compound amount for interest periods of other than 1 year.
Artists, minorities music, money makers, lip-syncing preachers, pretending holiness, video pictures like the word urban on itself. Dance with breakers, talent scouts gonna make you a star in your noise. Rappers only talking about the queen of fancy car. Wanna be original, psycho rocket, smashing guitar. Read the amendments, record shop, fantasizers, prize contests, organizers, creativity, vaporizers, household puppet supervisors, hands and click, televisor, quicker ships, customizer, major label, womanizer, wanna be CD, DJs playing on demand hits, commercial benefits, promotional disaster, dedication, bits, radio stations, drop-offs, the imitations, corporate simulations, crooked organization, open sessions, compression, on my verbal expression, one more beats, no question, home conventions, live the life, so can you take it, take it. Yeah. Daily routine, picture what your brain cells, crack individual domes like eggshells. With heaven and hell, mixed spells and calculations, got you forming masses by indoctrination. You want patience, so misinterpretation of religion, nation, claiming the nation, and political radical words that you bag up. Ignorant thought you get stoned when you act up. That's why they wanna keep you down. Supporting the powers like bowing down to a crown. But the land swallow the millennium back. Haven't you learned to write a Genesis apple like Adam? Catholic high school clothes are in trouble. When there's no racism, church dedications and runnel. The black boy with the ABC saying within a bag the same can't throw it off differently. Yo. Go in with the devil like Martin Luther. It's something Superman success. The broadcast my blast pins on the door.
Section 1.2, Compound Interest. The typical interest-bearing savings or checking account will be described by an investor as earning a nominal annual interest rate compounded some number of times per year. Investors will often find interest compounded semi-annually, quarterly, monthly, weekly, or daily. In this section, we will compare and contrast compound interest to the simple interest case of the previous section. Whenever interest is allowed to earn interest itself, an investment is said to earn compound interest. In this situation, part of the interest is paid to the depositor once or more frequently per year. Once paid, the interest begins earning interest. We will let n denote the number of compounding periods per year. For example, for interest compounded monthly, n equals 12. Only two small modifications to the interest formula in equation 1.2 are needed to calculate the compound interest. 1.2 being this. First, it is now necessary to think of the interest rate per compounding period. If the annual interest rate is R, then the interest rate per compounding period is R divided by N. Second, the elapsed time should be thought of as some number of compounding periods rather than years. Thus, with N compounding periods per year, the number of compounding periods in T years is NT. Therefore, the formula for compound interest is 1.3. Here we go. Equation 1.3 simplifies to the formula for the amount due given in equation 1.2 when n equals 1. Example 1.1. Suppose an account earns 5.75% annually, compounded monthly. If the principal amount is $3,104, then after 3.5 years, the amount due will be, here's this equation, and it will be 3,794.15. The reader should verify using equation 1.1 that if the principal in the previous example earned only simple interest at an annual rate of 5.75%, then the amount due after 3.5 years would be only $37.2868. Thus, happily for the depositor, compound interest builds capital faster than simple interest. Frequently, it is useful to compare an annual interest rate with compounding to an equivalent simple interest, i.e. to the simple annual interest rate, which would generate the same amount of interest as the annual compound rate. This equivalent interest rate is called the effective interest rate. For the rate mentioned in the previous example, we can find the effective interest rate by solving the equation and getting this. Thus, the nominal annual interest rate of 5.75% compounded monthly is equivalent to an effective annual rate of 5.90%. In general, if the nominal annual rate R is compounded n times per year, the equivalent effective annual rate R sub E, which is, the equivalent effective annual rate is given by the formula, this formula, 1.4. Intuitively, it seems that more compounding periods per year implies a higher effective annual interest rate. In the next section, we will explore the limiting case of frequent compounding going beyond semi-annually, quarterly, monthly, weekly, daily, hourly, etc., to continuously.
You got heart, sorrow, and life that you really frustrated. Don't love your wife, you teach and preach at the local high school. When they don't believe or ignore your group, you can't control your anger. They glue to the sky, confuse religious lies like they all think they're televised. Use highs for pupils, but they can tell, cause if they do calculate high school girls go to hell.
Section 1.3, continuously compounded interest. Mathematically, when considering the effect on the compound interest of more frequent compounding, we are contemplating a limiting process. In symbolic form, we would like to find the compound amount A, which satisfies the equation 1.5. Fortunately, there is a simple expression for the value of the limit on the right-hand side of equation 1.5. We will find it by working on the limit. There we go. This limit is indeterminate of the form 1 to the power of infinity. We will evaluate it through a standard approach using the natural logarithm and L'Hopital's rule. The reader should consult an elementary calculus book, such as, for more details.
L'hôpital. L'hôpital. L'hôpital.
Everyone does.
Boulevard de l'Hôpital. Boulevard de l'Hôpital.
L'hôpital. L'hôpital. L'Hopital's rule. We see that if y equals 1 plus r divided by n to the n, or if we start with this, then the logarithm of this equals the logarithm of this. And by the property of logarithm, this exponent can be dropped down. So logarithm of this to the n equals n times the logarithm of this. And then what you do is you say the n is equivalent to 1 divided by 1 divided by n. So you multiply by that, and you get 1 divided by n in the denominator. Which is indeterminate of the form 0 divided by 0 as n approaches infinity. To apply L'Hopital's rule, we take the limit of the derivative of the numerator over the derivative of the denominator. Thus, this limit, so the limit of this as n approaches infinity is the same as the limit of this as n approaches infinity by L'Hopital's rule. So when you take this derivative, you end up when you take the derivative of this and simplify, you end up getting this, and the limit as n approaches infinity is r. And since the limit of log y, log base e of y is r, then the limit of y is e to the r. There you go. Thus, the limit as n approaches infinity of y is e to the r. Finally, we arrive at the formula for continuously compounded interest, equation 1.6. A equals PERT. It's PERT. PERT. This formula may seem familiar since it is often presented as the exponential growth formula in elementary algebra, precalculus, or calculus. The quantity A has the property that A changes with time t at a rate proportional to A itself. Example 1.2. Suppose $3,585 is deposited in an account which pays interest at an annual rate of 6.15% compounded continuously. After 2.5 years, the principal plus earned interest will have grown to this formula being $4,180.82. The effective simple interest rate is the solution to the equation, this equation here, which implies that RE, which is the effective simple interest rate, is 6.34. So 6.15, and the new rate is 6.34. There should be a percent here. There you go. And I want to do the math real quick. I'm not 100% sure about this, so I'm just going to turn the music back on and run through the math. All right, that checks out.
Start this shit. What the fuck is this? Shit. We done really fucked up this time. Shit. Start this shit. Shit. What the fuck is this? Shit. We done really fucked up this time. Shit. Start this shit. Shit. Start this shit. Shit. What the fuck is this? Shit. He done really fucked up this time. Shit. What the fuck is this? Shit. He done really fucked up this time.
Foundation sound, ruler. I like scarring. Hold the order. Against certification fire. Take it away. We control it. We control it. We control it. We control it. Some of them deal with badness from upset and ill and hard and hard. Evil looks intention of it, tear us apart. Now we got them with the meaning, musically killing, and the template that was spinning coming straight from the heart. Now they remember and all like them, I reflect on them, not say that we have the best we cover in for the chart. It is separation coming to a radio station, build up on the foundation, call a machine in your heart. See the high views that we control it. We control it. We control it. We control it. We control it.
1.4, present value. One of the themes we will see many times in the study of financial mathematics is the comparison of the value of a particular investment at the present time with the value of the investment at some point in the future. This is the comparison between the present value of an investment versus its future value. We will see in this section that present and future value play central roles in planning for retirement and determining loan payments. Later in this book, present and future values will help us determine a fair price for stock market derivatives. The future value t years from now of an invested amount p, subject to an annual interest rate r compounded continuously, is this: a equals p e to the rt. Thus, by comparison with equation 1.6, the future value of p is just the compound interest of p monetary units invested in a savings account, earning interest r compounded continuously for t years. By contrast, the present value of a in an environment of interest rate r compounded continuously for t years is this formula: p equals a times e to the negative rt. In other words, if an investor wishes to have a monetary units in savings t years from now, and they can place money in the savings account earning interest at an annual rate r compounded continuously, the investor should deposit p monetary units now. There are also formulas for future and present value when interest is compounded at discrete intervals, not continuously. If the interest rate is r annually, with n compounding periods per year, then the future value of p is this formula: a equals p times 1 to the r over n to the nt, all to the nt. Compare this equation with equation 1.3. Simple algebra shows then the present value of p earning interest at rate r compounded n times per year for t years is p equals a times 1 plus r to the n divided by to the power of negative nt. Example 1.3. Suppose an investor will receive payments at the end of the next 6 years in the amounts shown in the table below. Here's your table. If the interest rate is 3.99% compounded monthly, what is the present value of the investments? Assuming the first payment will arrive 1 year from now, the present value is the sum. All right, so it was too many numbers. I didn't want to write them all, so I wrote this formula instead. The present value is the summation of this equation. A t 1 plus 1 plus 0.03399 divided by 12 to the 12 negative 12t. So the sum for example, for a sub 1, the first what are they called? Additive sum. What are they called? You have factor product, but what is it called? Addend. It's called an addend. There you go. It's called an addend. So the addends are the various are the values of this formula for different values of t. So for example, t equals 1. This is going to be negative 12. And a of t is going to, we're going to look at our chart. A of t is 465. For the next one, it will be 233. That's weird. 233, and this will be negative 24. This will be, for the next, this will be 36, and this will be 632, and so on. When you add these all together, when you add when you add the value of the formula for each value of t, the sum of those is the present value of this investment. Suppose an investor will receive payments at the end of the next 6 years in the amounts shown in the table below. So this is kind of like weird. So you can just like receive different amounts of money on a schedule, but like, you know, you can do the math. The math works out. It's fine. You can still calculate the present value because based on an interest rate. And this sum ends up being $2,003.01. And now what's important is to realize is that this the present value is usually going to be less than the value that just the sum of the payments in general, because money is worth more in the present than it is in the future. The same I don't know. Notice that the present value of the payments from the investment is different from the sum of the payments themselves, which is $22.77. Unless the reader is among the very fortunate few who can always pay cash for all purchases, you may someday apply for a loan from a bank or other financial institution. Loans are always made under the assumptions of a prevailing interest rate with compounding, an amount to be borrowed, and the lifespan of the loan, i.e., the time the borrower has to repay the loan. Usually, portions of the loan must be repaid at regular intervals, for example, monthly. Now we turn our attention to the question of using the amount borrowed, the length of the loan, and the interest rate to calculate the loan payment. A very helpful mathematical tool for answering questions regarding present and future values is the geometric series. Suppose we wish to find the sum indicated by 1.7. Sum equals 1 plus a squared plus ... plus a to the n, where n is a positive whole number. If both sides of equation 1.7 are multiplied by a and then subtracted from equation 1.7, we have, there you go, there's that, and then s minus as equals 1, and then subtracting, these cancel, all of these cancel, a sub n cancels, a to the n cancels, and then what's left is a negative a to the n plus 1. So s minus as is 1 minus a to the n plus 1. And so s, you factor out s here, and you get a 1 minus a, and you divide that to find s. This quantity can be rewritten as this formula. As long as a does not equal 1. And this is equation 1.8. Now we will apply this tool to the task of finding out the monthly amount of a loan payment. Suppose someone borrows P to purchase a new car. The bank issuing the automobile loan charges interest at the annual rate of R, compounded n times per year. The length of the loan will be T years. The monthly installment can be calculated if we apply the principle that the present value of all the payments made must equal the amount borrowed. Suppose that the payment amount is the constant x. If the first payment must be made at the end of the first compounding period, then the present value of all the payments is this sum. You factor out x to the 1 plus r over n to the negative 1. You factor that out, and you end up with a sum that looks like this. And so you use this formula, end up with this, and you end up with this here. You get this, which reduces to this. Therefore, the relationship between the interest rate, the compounding frequency, the period of the loan, the principal amount borrowed, and the payment amount is expressed in the following equation. Equation 1.9. There you go. Yep. Now we'll move on to part 2 of section 1.4. As an example of the equation used in the first part of section 1.4, if a person borrows $25,000 for 5 years at an interest rate of 4.99% compounded monthly and makes equal monthly payments, the payment amount will be $25,000 times 0.0499 divided by 12 times 1 minus the quantity 1 plus the quantity 0.0499 divided by 12, close quantity, to the power of minus 12 times 5, which is minus 60, close quantity to the negative 1, which equals $471.67.
2, 3, go. Let's go. G-Mart. Horrified and awed by what I was witnessing because the scenes of torment were so incredibly imaginative and different. There was every manageable thing going on there, you know? It's just, so you can think of the kind of torture and human misery that was happening in there. I was in kind of the center of the hall and looked in and saw this scene and I was like, whoa. And then I went toward this door and I kind of floated toward it and there was a sucking sensation near this door, kind of like a whirlpool. And I got actually sucked into the hell. There were people shrieking and screaming, and there were naked human beings stranded about this horrid landscape with pools of bubbling excrement, and there's boulders, and animals were torturing people, and people were torturing each other, and, there were creatures with pitchforks, and, erupting flame geysers, and it was kind of the artist's classic depiction of hell.
Well, let me stop you right there. This is the most detailed description I've ever heard. present to you the Ragnarok. Far from the wreck, there's no regret, no surrender. People of the world, we bring you a new sound, a new order. Remember, into the next millennium, a new sound, a new order. People of the world, we present you.
Okay. 1 point for part 2. Similar reasoning can be used when determining how much to save for retirement. Suppose a person is 25 years of age now and plans to retire at age 65. For the next 40 years, they plan to invest a portion of their monthly income in securities which earn interest at the rate of 10% compounded monthly. After retirement, the person plans on receiving a monthly payment and annuity in the absolute amount of $1,500 for 30 years. The amount of money the person should invest monthly while working can be determined by equating the present value of all their deposits with the present value of all their withdrawals. The first deposit will be made 1 month from now, and the first withdrawal will be made 481 months from now. The last withdrawal will be made 840 months from now. The monthly deposit amount will be denoted by the symbol X. The present value of all the deposits made into the retirement fund is this. So it's the sum. What is it the sum of? What is it the sum of? Where X, the monthly deposit amount, is denoted by the symbol X. The present value of all the deposits made into the retirement fund is this. Meanwhile, the present value of the annuity payments is this. This equals, this summation formula equals this other formula equals this quantity. And since this has to equal this, we have that X is approximately 27.03. This seems like a small amount to invest, but such is the power of compound interest and starting a savings plan for retirement early. If the person waits 10 years, i.e. until age 35, to begin saving for retirement, but all other factors remain the same, then this. Which implies that the person must invest $75.61 monthly. Waiting 10 years to begin saving for retirement nearly triples the amount which the future retiree must set aside for retirement. The initial amounts invested are, of course, invested for a longer period of time and thus contribute a proportionately greater amount to the future value of the retirement account. Example 1.5. Suppose two persons will retire in 20 years. One begins saving immediately for retirement, but due to unforeseen circumstances, must abandon their savings plan after 4 years. The amount they put aside during those first 4 years remains invested, but no additional amounts are invested during the last 16 years of their working life. The other person waits 4 years before putting any money into a retirement savings account. They save for retirement only during the last 16 years of their working life. Let us explore the difference in the final amount of retirement savings that each person will possess. For the purpose of this couple, we will assume that the interest rate is R equals 0.05 compounded monthly, and that both workers will invest the same amount X monthly. The first worker has, upon retirement, an account whose present value is this. The present value of the second worker's total investment is this. Thus, the second worker retires with a larger amount of retirement savings. However, the ratio of the retirement balances is only 43.423 divided by 108.102, which is approximately 40%. The first worker saves in only 1/5 of the time, approximately 40% of what the second worker saves. The discussion of retirement savings makes no provision for rising prices. The economic concept of inflation is the phenomenon of the decrease in the purchasing power of a unit of money relative to a unit amount of goods or services. The rate of inflation, usually expressed as an annual percentage rate, similar to an interest rate, varies with time and is a function of many factors, including political, economic, and international factors. While the causes of inflation can be many and complex, inflation is generally described as a condition which results from an increase in the amount of money in circulation without a commensurate increase in the amount of available goods. Thus, relative to the supply of goods, the value of the currency is decreased. This can happen when wages are arbitrarily increased without an equal increase in worker productivity. We now focus on the effect that inflation may have on the worker planning to save for retirement. If the interest rate on savings is R and the inflation rate is I, we could calculate the inflation-adjusted rate, or as it is sometimes called, the real rate of interest. This derivation will test your understanding of the concepts of present and future value discussed earlier in this chapter. We will let the symbol R sub I denote the inflation-adjusted interest rate, Broverman 2004. Suppose at the current time, 1 unit of currency will purchase 1 unit of goods. Invested in savings, that 1 unit of currency has a future value in 1 year of 1 plus R. In 1 year, the unit of goods will require 1 plus I units of currency for purchase. This difference, 1 plus R minus 1 plus I, equals R minus I, will be the real rate of growth in the unit of currency invested now. However, this return on saving will not be earned until 1 year from now. Thus, we must adjust this rate of growth by finding its present value under the inflation rate. This leads us to the following formula for the inflation-adjusted interest rate. R sub I equals R minus I divided by 1 plus I. (1.10). Note that when inflation is low, I is small, R sub I is approximately R minus I. And this latter approximation is sometimes used in place of the more accurate value expressed in equation 1.10. Returning to the earlier example of the worker saving for retirement, consider the case in which R equals 0.10. The worker will save for 40 years and live on a monthly annuity whose inflation-adjusted value will be $1,500 for 30 years, and the rate of inflation will be I equals 0.03 for the entire lifespan of the worker retiree. Thus R sub I equals 0.0680. Assuming the worker will make the first deposit in 1 month, the present value of all deposits to be made is this sum. The present value of all the annuity payments is given by this. Thus, the monthly deposit amount is approximately $92.71. This is roughly 4 times the monthly investment amount when inflation is ignored. However, since inflation does tend to take place over the long run, ignoring a 3% inflation rate over the lifetime of the individual would mean that the present purchasing power of the last annuity payment would be this. This is not much money to live on for an entire month. Retirement planning should include provisions for inflation, varying interest rates, provisions for inflation, varying interest rates, the period of retirement, the period of savings, and desired monthly annuity during retirement. All right, that's enough.